Hey guys, Andre Freeman here. I want to go through a quick example of how we can construct actually a discrete probability distribution from a frequency distribution. Let's look at the definition of a discrete probability distribution. This is a probability distribution that shows all possible values of a discrete random variable along with the associated probabilities. So here we have a histogram or bar graph that shows the counts for each of the ratings. 1,000 people were asked the question, do you enjoy music? And they were asked to respond with either 1, strongly disagree, 2, disagree, 3, neutral, 4, agree, 5, strongly agree. So again, 1,000 people were surveyed, and each person had to respond with a 1, 2, 3, 4, or 5. So the graph shows the counts. You can see that 9 people said they strongly disagree, 11 said they disagree, 36 said they're neutral, 122 said that they agree, and 822 people said that they strongly agree with the statement, I enjoy music. We can create a frequency table from this graph. And now what we want to do is we want to convert each of these frequencies to probabilities. And we can do that by computing the relative frequency. The relative frequency would be the frequency divided by the total frequency. So let's take a look. So for the random variable value 1, the relative frequency will be 9 divided by 1,000, and that's going to be, as a decimal, 0.009. The next one would be 11 over 1,000, and as a decimal, that would be 0.011. 36 over 1,000, that as a decimal would be 0.036. Let's see, 122 over 1,000. This as a decimal would be 0.122. And lastly, we have 822 divided by 1,000. And that as a decimal, we have 0.822. So these values are the probabilities. And we want to kind of pause and make sure we can interpret what we're saying. Let's start with the first row. We can say that there is a 0.009 chance that a person would respond 1, that they strongly disagree. And we can write these actually as percentages as well. So this would be 0.9%. This is 0.11%. This is now 3.6%. This is 12.2%. And this is 82.2%. And if we add up all of these percentages, we're going to get 100%. So one of the key features of a discrete probability distribution is you have a list of each value that the random variable can take. The random variable here can take on 5 values, 1, 2, 3, 4, or 5. Each of the values has a probability. So each value of the random variable has a probability. And the sum of the probabilities is 1. So another interpretation, if we look at the fourth row, we can say that if we randomly pick a person in this sample, there's a 12.2% chance that they would say 4, they would respond 4, that they agree with the statement. Whereas if we randomly pick a person in this sample, there is an 82.2% chance that they would respond 5, that they strongly agree with the statement that they enjoy music. So what we've done so far is we've constructed a discrete probability distribution. Let's go a step further and look at how we can now compute the mean or the expected value. And what this requires that we do is take each value of the random variable and multiply it by the probability, by its probability. And we're going to add up those products. And what we're basically computing is a weighted average of these values of the random variable using the probabilities as weights. This calculation of the expected value is truly a weighted average. Again, what is the average of these values of the random variable when we use probabilities as weights? So we're going to take each number and multiply it by its probability and add up all the products. So what would that look like? So we'll do 1 times 0.009, and we can use the decimal value, plus 2 times 0.011, plus 3 times 0.036, plus 4 times 0.122, plus 5 times 0.822. So this weighted average using probabilities as weights will give us the mean of this discrete probability distribution. So let's put this in Desmos and see what we get. So Desmos is great for doing these types of calculations. And we can see here when we plug this into Desmos, the scientific calculator, we get a value of 4.737. So 4.737 is the expected value for this discrete probability distribution. And we can interpret this in a couple different ways. What we can do is we can say that a couple ways of interpreting this. One interpretation would be that if we select a person from the sample, the expected response is around 4.7. Now, it's impossible for a person to, so this is essentially the guess, the best guess we have. Now, if we select a person, they would never respond 4.7 because 4.7 is not a possible response. They would either respond 1, 2, 3, 4, or 5 based on the scale. And 4.7 is closest to 5. So what we can say is, well, if we had to guess, our best guess would be that a person in this sample would respond 5, right? That's our best guess to what the typical person would respond. It's also our best guess to be what a randomly selected person in the sample would respond. So I'll add here which is closest to 5. So this is kind of the expected value. What do we expect to get if we pick a person at random? What random variable value would we expect to see? The next interpretation is the long-term average. So let's talk about this. Now we're saying if we pick somebody and we find out that they selected 4, and we pick another person and we find that they selected 5, and we pick another person and they selected 3, and we select another person and they selected, let's say, 2. We keep a running total of the responses from individuals we observe. The long run cumulative average would be 4.737. So that's the idea of, if we repeat the experiment many, many, many times, what would be the long run average of the observations? What would be the long run average of the random variable values? All right, guys, I hope this helps.